Alright, welcome back everybody. In this video we're going to continue with section 6.9 of AP Calculus, integrating using substitution. And we're going to look at stuff from the integrating using substitution part 2 lesson. I'm going to take the training wheels off instead of the substitution being given. Alright. We're going to first need to figure out what that substitution is, what our best choice of substitution is. So look at the integral in example 1. Integrate the integral of sine of the quantity 1 minus x times the quantity 2 minus the cosine of the quantity 1 minus x. All of that raised to the 4th power. Whew. Now there are a lot of different choices as far as things I could use as a substitution here. Let me just list a bunch of things that maybe I could choose. I could choose the sine of 1 minus x. I could choose just the quantity 1 minus x. I could choose the quantity 2 minus the cosine of the quantity 1 minus x. I could choose the cosine of the quantity 1 minus x. Let's see, what else could I choose? I could choose the quantity 2 minus the cosine of the quantity 1 minus x, all that raised to the 4th power. I think I've got pretty much everything that anybody might want to choose as far as a substitution here. So now the question is, which of these is best? All right, and we want to try not to substitute too little or too much. You know, if we try and substitute too much, we'll end up in a position where when we take du, we don't have anything left in the expression to substitute. On the other end of the spectrum, if we choose, too little, like in this case, I would say substituting the quantity 1 minus x, that will work, but I want to get a little bit more of a bite into this now. And what I mean by that is if I substituted the quantity 1 minus x, that would totally work. Absolutely, it would work. But what would happen is I would simplify this and I would still be in a position where I needed to make another substitution after making that one. So thinking about why we use integration by substitution can be helpful here. We use integration by substitution in order to deal with the implications that come from the chain rule. And so usually our best bet as far as a substitution is that we pick something that is inside of a composition of multiple functions. Now I already said that 1 minus x was probably a poor choice. So I want something that is inside of another function. And I think looking at this, I think that the best substitution is going to be u equals 2 minus the cosine of the quantity 1 minus x. Now, why did I pick that? I picked that because it's the entire expression that's inside these parentheses that's being raised to the 4th power. And so that is definitely something that is inside of a composite function. Now that I've picked that as my substitution, I'm going to proceed from there. And sometimes you'll pick a substitution and it just won't work. Sometimes you've got to, grind on these problems a little bit where you'll pick a substitution, you'll try to simplify it algebraically, and you'll see, uh-oh, this isn't going to work for me. So you try something else. And, we'll learn some additional techniques for, weird, unusual situations. But you always want to try something and see how it works. So I'm going to try u equals 2 minus the cosine of 1 minus x. I take the derivative of this. The derivative of 2 minus cosine of 1 minus x, the derivative of cosine is negative sine. So I'm taking the opposite of negative sine of the quantity 1 minus x, and then applying the chain rule times the derivative of the inside. The derivative of 1 minus x is negative dx. And so du here is equal to, till I sort out all these negative signs, it's the opposite of the sine of the quantity 1 minus x dx, which comes very close to what's left in this problem, the quantity sine of the quantity 1 minus x dx. And so I can replace all of that green highlighted stuff with the opposite of du and turn this into the integral or the opposite of the integral of, and I've got u to the fourth du. So it looks like that was a great substitution for us. Now we're going to find the antiderivative. The antiderivative of u to the fourth is u to the fifth over 5 plus c. And then we're going to go ahead and distribute the negative sign and bring u back. And boom, there is our indefinite integral in example 1. All right, example 2. We want to integrate the integral of cosine of the quantity 3z times sine to the 10th of the quantity 3z dz. It might be helpful for us to think about this problem as cosine of 3z times the quantity sine of 3z raised to the 10th dz. I think by thinking about this problem that way, it almost becomes apparent to me what I want to use as a substitution, because I want to use something that is inside of another composition, is inside of a composition of multiple functions. And it looks like the best choice here. I think I want to use sine of 3z as my u in this problem. So if u is equal to the sine of 3z, that means du is equal to 3 cosine of 3z dz, which is almost what I have left here. It's cosine of 3z dz. So I'm going to replace that with a 1/3 du. And that turns this integral into 1/3 times the integral of u to the 10th du. Finding my antiderivative, this is 1/3 times u to the 11th over 11 plus c. I distribute my 1/3 through, gives me u to the 11th over 33 plus c. And then I bring my u back. That's sine to the 11th of the quantity 3z all over 33 plus our constant. All right, example 3. We have multiple terms in example 3. We're integrating the e to the 2t plus secant of 2t, tangent of 2t. Looking at these two terms, it looks like what's inside of both of these is just u equals 2t. And so I can replace this 2t and this 2t and this 2t. I can replace all of those with u's. So du is 2 dt, and so 1/2 du is equal to dt. And so I can replace this dt with a 1/2 du. I often wonder if you can hear fire engines when they go by my house when I'm talking on my microphone, but I guess we'll find out. So I'm going to replace the dt with a 1/2 du and rewrite this 1/2 times the integral of e to the u plus secant of u tangent of u du. And then I can take the antiderivative of this term by term. It's going to be the integral of e to the u is e to the u. The integral of secant of u tangent of u is just going to be secant of u. And don't forget your constant of integration. And then we will bring back our substitution. So we've got e to the 2t plus the secant of 2t plus c. That takes us to the end of example 3. Example 4 is very similar. It's the sum of two things, but in this case, one substitution is just not going to work because we've got two different things that we're substituting. So what do we do in a situation like this where we've got multiple terms and different substitutions are appropriate? Well, when we have the sum of two things, if you remember back when we talked about properties of integrals, we said that we could take the integral of f of x plus g of x, and that was equal to the integral of f of x plus the integral of g of x. And so I can convert this into the integral of e to the negative z dz plus the integral of secant squared of z over 10 dz. And then I can use two separate substitutions for these integrals. For the first one, I want to use u equals negative z. So then du is negative dz, and I can replace dz with a negative du. So this turns that integral into negative e to the u du. And then for the other integral, what's inside the composition is z over 10. I don't want to use u because I already used u once in this problem. I'm going to use t instead as my replacement here. And so we're going to replace t with z over 10. So dt is 1/10 dz. And so I can replace dz with a 10t, and this turns into 10 integral secant squared of t dt. And now that I've rewritten both of those using those substitutions, I can go ahead and take the antiderivative. It gives me negative e to the u plus c plus 10, and the antiderivative of secant squared is tangent of t, plus another c. Now what I'm going to do with these constants, since there was one constant from each integrand, I'm just going to combine them into a single constant in my final answer. And now I'm going to bring all my letters back. I've got negative e to the u. U was equal to negative z. I've got 10 tangent of t. T was equal to z over 10. And then I combine those constants into a single constant of integration. And there's the integral of e to the negative z plus secant squared of z over 10 dz using multiple substitutions. All right, that brings us just about to the end of this video. We're going to come back next time and look at a few more examples of substitution in this lesson. And so we'll see you then. Everybody have a great rest of your day, and I'll talk to you next time. Bye-bye.